In this video, I'm going to go through the steps to solve for the current as a function of time in an RLC series circuit that has a voltage that is not a constant but is a sine function. So it's known as a driven circuit. So here's the variables we'll be using. V of t is going to be our voltage, and that's going to be initialized or defined as a constant V naught, the maximum voltage, times a sine function with a frequency of omega, and t is the independent variable time. In our circuit, we have a resistor with resistance R, inductor, inductance L, capacitor, capacitance C, all wired in a circuit as in this diagram. So what do we mean by solution? What are we solving for? Well, like I said, that's the current. It's the amount of charge flowing through any part of the circuit per unit time. That's denoted by big I of t. And so we're going to solve this differential equation that we're going to set up. And so I of t is going to be dependent on what we choose for V of t, R, L, and C. So I'm not going to go much into the physics behind circuits and E&M, but I'm just going to use one of Kirchhoff's laws to set up the differential equation. So Kirchhoff's voltage law says that the sum of the voltage drops across the circuit is equal to the voltage being provided. So there may be a more accurate or correct way of phrasing that, saying that, but the basic idea is we can set V equal to L times di dt, which is the voltage drop across the inductor, R resistance times I for the voltage drop across the resistor, and Q over C for the voltage across the capacitor. Alright, from now on I'm kind of going through a mathematical perspective, just not really interested that much in physics, but more using these variables as just numbers, mathematical entities that don't have much significance. I know I'm aware that there's many ways to talk about this circuit and understand its properties, but I'm not really going to go into the physics. So our equation has a variable right now that's q, and we want to reduce that variable or change it into something in terms of I, because q is charge, and we're interested in solving for current. So we know the relationship between current and charge. So current I is the time derivative of charge. And using this relationship, we can eliminate this q and move forward with the equation just involving I and the parameters L, R, C. So notation-wise, we're going to drop the ddt's, and we're just going to use this prime notation for time derivative to make things cleaner to see. And so rewriting the Kirchhoff's voltage equation, we've substituted in the V of t, the voltage, as a time-dependent sine function. And this is just simplifying notation, dropping the t's in the I of t's and q of t's, and using the prime notation for time derivative. Alright, so the second major thing that we're going to do is we're going to differentiate the entire equation with respect to time. And the point of doing this is so that we can get rid of this q and look at something in terms of I, just the current. So when we take the time derivative of both sides, using the chain rule, this omega frequency pops out, and sine turns into a cosine. On the right-hand side, it's fairly simple. The I prime turns into I double prime, I turns into I prime, and q turns into I, since I is defined as the time derivative of q. Now, one thing to pause and just think about for a brief moment when I looked at this and just considered it. So whenever whenever something is changed from the original setup, I always questioned, I have the urge to question, why are we not doing things based off the original one? And is it okay that we've changed the problem that we're solving? Does it still match? Does it still solve the original thing that we're looking for? And it might not be hard to see, or it may be trivial, but so here are the thoughts that I come up for it. Well, for the obvious reasons, the original equation is about charge q, so we're looking to solve for I, and so we want our unknown variable in terms of I. So taking the time derivative changes q to I. That's the motivation. So that's the reason why we did it, and we're not solving the original equation because it has a q in it. And what are we going to do with q? As it is, well, it doesn't really help us look for I. So the second part is, all right, is it still correct? We're solving something different from the thing we originally set up. Is it still a accurate representation of what we have originally? Or like, is it still solving the problem we first defined? Or like, hopefully we're not looking for a solution to something that's unrelated to what we started with. A solution that's correct, but not to the problem we're interested in. And for that, it is correct to look at this derivative equation, and it's fine because this derivative equation, it has to be true given this first equation. So if this is something that we take as true, then this follows as a consequence. So this is never wrong. This is always correct as long as this is okay. The second one is always okay, as long as the first one is okay. Have we changed anything? No. I mean, we've taken a look at a property of this first equation, in a sense, like we're taking its derivative. So we're looking at another property of the first equation, and then through that we can solve for I, the thing that we're interested in. The problem would arise if we are starting with a second equation. Let's say somehow we set this up and we found this to be true, and then we want to integrate and go back up to this first equation to say that this applies to our situation. Well, then there might be a problem, because knowing when we integrate there is a arbitrary constant that is introduced. Since we don't know enough about the original setup, there can be infinitely many that differs by an arbitrary constant. So if we were to integrate, there might be an issue because we might be solving something that is not accurately reflecting what we started with. But we're going in the downward direction. We're taking a derivative and solving that. So there's no issue because the second equation is always correct given the first equation. A bit of a digression there. So if it's not really significant, then you'll have to pardon me, but it's something that I like to consider. So we set up the equation we need to solve for I, and this is starting the differential equation solving part. it's going to involve solving two different equations that are related. So they're not really that much different. This procedure has a name, and it goes by the name of method of undetermined coefficients. And the type of differential equation we have that we're solving can be described as second order, non-homogeneous, linear ordinary differential equation. And that's a mouthful of words. It's not really saying much, but it gives a nice way of reference to look up something by a categorization other than just plugging in exactly the differential equation that you're trying to solve. If you're looking for a general approach or like some kind of background reference to say, all right, in this situation, what do I do? Then it's nice to have a name to look up so that you can do some more research. But second order basically means that the highest derivative is second derivative. Non-homogeneous means that the derivatives on one side are all on one side. The function and its derivatives are all on one side. On the other side is the particular function that we're interested in. And if this is not zero, then the differential equation is called non-homogeneous. If the part over here, this left-hand side that we set up here, is zero, then that's a homogeneous equation. Linear just refers to the fact that all these functions of I and its derivatives are added together. So it's a linear combination of various order derivatives of the function that we're solving for. And ordinary differential equation refers to the fact that these derivatives are straightforward whole derivatives. They're not partial derivatives. So our function I is just a function of t. It's one variable, and we're taking the total derivative in terms of t. All right, that gives us some kind of narrowing down of what we're dealing with, kind of understanding what the nature of what we're solving is. And so the solution goes in two parts. We're going to set up equation based on what we found with Kirchhoff's law, but we're going to replace the particular part, this frequency omega v naught cosine omega t. We're going to replace that with 0, and this creates what's called the homogeneous equation. And homogeneous, once again, just refers to the fact that it's a 0 on this side. That's equal to the function of this unknown I and its derivatives. So we're going to solve this homogeneous equation first. And then that's going to be 1/2 of our solution. Whatever we find solves this homogeneous equation is going to be 1/2 of our final solution. And then we're going to plug back in this omega v naught cosine omega t, this particular part, and then that's the particular equation that we're going to solve. We're going to solve it again using that plugging back in that particular part, and that's going to give us the second half of our total solution. And the reason that we need two parts, I should talk about a little later, but basically if we find something that solves the homogeneous equation, adding that to our answer is not going to affect the left-hand side because we're just adding 0 to it. So in order to get the most general solution, we always have to add this homogeneous solution to whatever particular function solution that we have. Alright, so let's get solving a little bit and find these homogeneous particular solutions before we piece them together and see why they're necessary to have both parts. So to solve the homogeneous equation, we could just introduce the correct function and show that it solves it and say, all right, look, when you got this, here's what you use, and be done with it. But for me, that's not really a satisfying enough approach to understanding a problem, because I have to take for granted what you're saying is correct if you just tell me that this function will solve it and that's what we use. So what I'm trying to do here is go through kind of a thought exercise, or some of the thought process behind why we should pick the function that we're given and why it makes sense. So the function is e to the kt, where k is a constant, and hopefully this kind of gives us an idea of how we get there. The first section that I've created is thinking about what happens if we just have a differential equation involving I. That's not really a differential equation, it's just an equation saying I equals 0. But if we have a first derivative of the function I, and that equals 0, well, we just integrate it, and then that means I of t is a constant. Very simple, it's not really differential equations, it's just calculus integration. Same thing if we have I double prime equals 0. I then is a constant times t. Well, what's the point of this? Well, the idea that I'm kind of trying to get at is when you just do simple integration of polynomials like that, each time you have a different order derivative, you're going to get a different order result coming out of it. And when I mean order, I mean like t to the n. So if it's a polynomial, you have t to the n, and you take it in antiderivative, it becomes t to the n plus 1. So it becomes a higher order when you solve by integrating. And so the point is that what we started with I, turns into something different when we do derivatives to it. It becomes t to the n plus 1 or n plus 2, or something that's not just t to the n anymore. Not t to the n anymore. So what we've got in our equation is several constants times different derivatives of I. We got a second order derivative, a first order derivative, and the function itself. So in order for them to add up together to equal 0, that kind of means that they all have to cancel out somehow in the end. And in order to cancel out, we have to be dealing with things of the same type, of the same order, or the same flavor of function, right? So if we do simple integration, we get stuff that's no longer what we started out with. But in order to have them all canceled out, we have to end up with the same type that we started out with. So I has to be the same type as I prime and I double prime. And to do that, we can't use a polynomial function. We have to look at a different function with more interesting properties. So here, let's suppose that our function was just a simple one, I prime plus I, and that equals 0. Well, one function that comes to mind is e to the x, or some flavor of e to the x. And because when we take its derivative, when we take the derivative of e to the x, I used x instead of t, forgive me, they should be all t's if I were consistent. But if we have some function like e to the t or e to the x, and we take its derivative, we get back itself. So now I prime and I are of the same flavor, variety, order, or type, or whatever the correct terminology I should use for it. But it's the same stuff. So there's a potential possibility for them to cancel each other out. And so e to the negative x, when we take its derivative plus itself, we're going to get negative e to the negative x plus e to the negative x, and that gives us 0. So e to the negative x solves this simple situation. All right, so what about when we have I double prime? Can we think of another function that solves that? And we know that sines and cosines have this interesting property that when you take its first derivative, you get the other one. But when you take another derivative, you get back what you started, right? So sine becomes cosine becomes negative sine. The only difference is there's a negative sign in front of what you started out with. The negative sign being like negative, not like sine function. S-I-G-N instead of S-I-N-E. Too many signs here. So sine and cosine would solve this because taking its double derivative gives the opposite. It's negative back. But another function, e to the ix, where I is the imaginary number I, it's a complex number I guess, also has that property. And really, sine and cosine can be expressed in terms of e to the complex number x. Some combination of e to the something x's. And from complex analysis, you can show that e to the ix can be expressed with sines and cosines, cosine plus I sine. So this kind of creates like this family of functions that will do the job. And because the key point is that when you take its first derivative, you get back something of the same order or the same type that you started with. And when you take its second derivative, you also get back kind of what you started with. So there's a possibility for adding them together in a certain combination to cancel each other out. All right, another rather long comment about this before we get to the meat of it. The function that we're going to use, that we're going to guess, is the function I of t equals e to the kt. K is a constant, but it can be a real number or a complex number. We don't really have to worry too much about it being real or complex right now. It's just think of it as a constant. So we get back to the starting point is use this. Why? Because when you take its derivatives, you get back the same type that you start with. And so there's a possibility of adding a combination of them so they all cancel out. And hopefully this digression or discourse or whatever, this little long bit about trying out different solutions gives somewhat of an intuitive understanding of what's going on or the reasoning behind using this function. All right, so we're going to go with it. We're going to take this and we're going to say whatever our solution is, it's going to look like this, e to the kt, and we're just going to plug it into the equation. So when we do I double dot, I is e to the kt. That means I double dot is k squared e to the kt. So we're going to get a k squared here. The L is still a constant in front of it. And the e to the kt is here, but I factored this out so that we have a cleaner solution to look at. And because all the other ones are going to also contain e to the kt. So the second one is r prime. And that's going to give us r still, but extra k from the taking the derivative. And 1 over c times I is just 1 over c. And then so outside we have e to the kt. All right, this gives us a new equation to look at. And we have something else to notice, something to say about this. is that the function e to the kt is always a positive function. For any t that we choose or any constant k that we pick, this function graphed here is never zero. It's never equal to zero. So when we have this function times something else equal to zero, by the zero product property saying that one of these guys has to equal zero, well, it can't be e to the kt, so it's got to be all this other stuff. We can state 0 equals L k squared plus RK plus 1 over C. Now this is a simple quadratic equation in terms of the unknown k, so we can use our by now memorized quadratic equation formula. Negative b plus or minus square root of b squared minus 4ac all over 2a. Yeah, so when you plug all this stuff in here, that's what we get. And the plus or minus tells us, well, we don't have one solution, we have two. So we have a k1 and a k2. And one of them has a positive, one of them has a negative. Well, we said that this e to the kt was the solution, right? But now we have two k's that are possible. Which one's correct? Which one do we take? Which one's more correct? Well, they're both correct. They're equally correct. But they're not, neither of them are the entire solution to the homogeneous part. So actually what we're going to do is we're going to take a linear combination of them. And that just means that we're going to take some constant times the e to the k1 part times t solution, and we're going to add it to another some constant c2 times the e to the k2, this other k solution times t function. So why is this okay, and why is this necessary to be more general? Well, the idea is that if one of the e to the k1, if one of the e to the kt's is a solution, then adding e to the kt to itself is another solution. And adding another e to the kt to that is another solution, and so on, saying that any multiple of e to the kt is also a solution if e to the kt is a solution. Why does this happen? So this is kind of like a circular reasoning almost. It happens because it has this property. But so the differential equation, this right hand side, this stuff here, it's a linear equation. It's a linear function. And not linear in the sense that it's a constant times x, y equals cx. But linear in the sense that if we were to plug in a plus b as the input, what we get out is the same as taking the function of a plus the function of b. So what I'm trying to verbally state is this property here. And that's what makes it linear. Adding the output of the function when we plug in x separately from when we plug in y, when we add these two together, it's equal. It's the same as if we just plug them all both together, the sum of x and y, into the function. Why does this happen in our case? Well, because we know from calculus if we take the derivative of a sum of two quantities, it's the same as summing the derivatives of the two quantities. So taking the derivative preserves its linearity, quote unquote. And the other part is that we're just adding them. We're adding these different derivatives times stuff. Multiplying by a constant is commutative, so constant times x parentheses x plus y is the same as L times x plus L times y, etc. So there's nothing going on here that's like multiply two things together. There are different variables, or do something fancy. It's just basically adding stuff together. So it's a linear function. So the other part of why any multiple of this e to the kt solution is also a solution is because the function itself equals 0. All this stuff here, this function that we're calling all this right-hand side of the differential equation, is equal to 0. So if we plug in x, or if we plug in y, or if we plug in x plus y, the result is always 0. So if x solves it, y solves it, x plus y also solves it. Because each time we plug in something, we get back 0. So this is like 0 plus 0 equals what happens when we plug in x plus y. So that means x plus y also solves the equation, because the function of it equals 0. This wouldn't happen if the left-hand side of the differential equation was some number, some constant, because each time we plugged in what we had as a solution, well, the result of adding another solution to what we plug in would increase the output of the function. So this two parts of why any multiple of a solution e to the kt is also a solution. Number one, because the right-hand side differential equation is linear, and the second part is that the left-hand side is equal to 0. Alright, so any multiple of e to the k1t is also a solution, but by the same logic, if e to the k2t is a solution, then we could also add e to the k2t any number of times, and the result of the function would also still be 0, so it would solve the differential equation that we've set up. And these just kind of listing what we have. Either k1t is a solution, either k2t is a solution. That means we can add e to the k1t to itself any number of times and have a solution. We can have k1 and k2 added together to be a solution, or we have k2 added to itself any number of times to be a solution. So for our solution to capture all those possibilities, we have to have some combination, linear combination of e to the k1t and e to the k2t. Now c1 and c2 are constants, but here we don't explicitly state what they are, and that's because what they are depends on our initial conditions of our circuit. So I think what comes to mind is the initial charge on the capacitor, and the initial current. That sounds like what it would be, but I'm not going to go into solving for initial conditions in this video. So we just leave them as unknown, undetermined, but undetermined coefficients that are dependent on initial conditions. They're not variables, they're like still constants, but we haven't figured out what they are because we don't have enough information right now. So they're not variables. All right. This is the result of what we've done, is find the homogeneous part of the solution. And that's one half of our final answer. The second half of our final answer is going to be solution to the particular equation when we plug back in this frequency v0 cosine omega t. And this is actually like the real equation that we set up, right? The other one was kind of like, all right, let's eliminate this guy and pretend it's 0 and then see what solves it. And it's like, that's like the fake one. This is like the real one. This is the real deal. Okay, so how do we figure out what function to put in this time? The other one we put in e to the kt because of this kind of whole reasoning that what the order of what we plug in should be the same as what when we plug in the function, taking any of its derivatives, first or second, should give back something of the same type that we started with. All right, that was our rationale, because in order for it to be equal to 0 on the left-hand side, they all have to cancel, so they have to be of the same type. All right, whether or not that was a successful explanation of the reasoning or not, here we have a different situation. So what we have on the left-hand side is not equal to 0, so that doesn't mean it doesn't mean that we can use the same logic, say they all have to cancel out, so they all have to be e to the kts. And so we have to use some kind of strategy, and this whole naming stuff that I mentioned earlier, this is kind of like, all right, so the strategy tells you what to do. Some mathematicians or smart people or whoever decided how things should be decided, all right, when you have this situation and you're using this method called method of undetermined coefficients, this is what it means you do. And basically, I'm sure there's a reasoning behind this that has some kind of proof backing it. But at this level of just starting differential equations, it's not really presented anywhere. But so basically it means guess. And what you're going to guess to be your solution is you can try to find the most general form of what you see on the left-hand side here. Whatever particular function that you're trying to solve for, you're going to create the most general form of it that you can think of and then guess that as your solution. So in our case, what most general form means is if we're dealing with a cosine, that belongs to the family of sines and cosines. So we're going to guess a combination of sines and cosines. And it's going to have some coefficient from the sine, some coefficient in front of the cosine that we're going to try to find out what it should be in order to solve the equation. All right, so this is all like dictated to you. This is what you're supposed to do. Why? It kind of makes sense because if you get out a cosine, you should start with something that's sine or cosine. And because sines can cancel out with other signs when you take derivatives and stuff like that, you can't rule them out. They could be lurking there. Even though your final solution is just a cosine, you can't just plug in a cosine to guess because, well, maybe you start out with sine and something happened to it. It just disappeared as you were canceling stuff out. So in order to be safe and be general, use both sines and cosines. Beyond that, I don't really have much of a proof like that this works, that this is what you should do. Like, it's kind of guesswork. At differential equations, at some point you're going to have to guess something. because there's no like clear path that dictates this is how you get back your solution. You just have to try different things that would make sense to try, and then once you guess correctly, you have to see if that solution matches your setup. So I basically don't have much to offer beyond that. Alright, we're going to guess the general form. And so that means I of t with this p subscript denoting that's the particular solution. Particular, again, denoting that this is plugged back in the function here. Homogeneous was when it was 0. We're going to plug in a sine omega t plus b cosine omega t. Alright, let's do that. But actually, on second thought, what if instead of using sines and cosines, we use a different form of that? So what we're going to do, because it's going to turn out to be more convenient, is we're going to use an equivalent form of sines and cosines. And that's a sine omega t minus phi. So you can do some trig identities to show that it's equivalent. Any expression you have in this form, a sine omega t plus b cosine omega t, can be expressed in the left-hand form, a sine omega t minus phi, for some a and phi. And this big A and phi are going to be different from little a and little b, but they have a relationship that you can manipulate to go from one to the other. Alright, so we're going to plug in this. We're going to use sines and cosines as the most general form, but the form is not going to involve any cosines. It's going to look like this, even though the cosine is equivalent to this form. So plugging in for I, this stuff here, a sine omega t minus phi. Left-hand side is not going to change, still what it is. But the right-hand side, we're going to take double derivatives, so that's going to bring out some extra omegas in front here. And then this is the stuff that we get. We're just going to leave it for now, but we're going to focus on the left-hand side. And now it's time for something clever. We're going to do something to make this left-hand side look more like the right-hand side so that we can compare different values. So there's a trig identity involving cosines. When we take the cosine of a plus b, we can rewrite that as cosine a cosine b minus sine a sine b. And we're going to use that in our case, but we're going to do something that's a little sly. We're going to rewrite this omega t as omega t minus phi plus phi. So when we subtract and add the same value, it doesn't affect what we have. But usually that's pointless. In this case, though, it allows us to have two things to add together. So the first part that we're going to have is omega t minus phi, and that's going to be what we plug into A. And the second part is phi itself, we're going to plug into B. And we're going to use this identity. So A becomes omega t minus phi, B becomes phi, and then what we have on the left-hand side goes through the identity and turns into this. And what do we have? Well, we've got something that's a coefficient in front of a cosine omega t minus phi term, plus some other constant times a sine omega t minus phi term. And why did we go from something that looks simple to something that looks complicated? Because it more matches what we have on the right hand side. And our right hand side has terms that are coefficients times sine omega t minus phi plus another coefficient times cosine omega t minus phi. So these sines and cosines now match on both sides of the equation. This allows us to compare the coefficient values. And for the equation to be equal, we can now set up two equations that equate, set the coefficients equal to each other. So we're going to say the coefficient in front of the cosines are equal, and the coefficients in front of the sines are also equal. Now, why can we do this? And this is what comes to my mind first of all when I see this is we have one equation, and now we're setting up two equations and saying that the first half is equal to the first half, second half is equal to the second half, because they're coefficients of the same functions. But if I question, like, what makes that okay? So the thought that I went through is as follows. It's okay because we're dealing with functions sine and cosine, and they are orthogonal to each other. In this case, I feel like they're behaving like independent basis vectors. So we have this kind of like space, this mathematical space, and you're defining functions on it using sines and cosines. So for the thing on the left side of the equation to be equal to the thing on the right side of the equation, you can only get them to be equal if you use the same weight on sine and cosine as you do on one side as the other side, because sine and cosine are like independent. So talking through this, I will definitely screw up on terminology and correctness and reasoning. I'll probably mess up. So I just try to use kind of a more simple analogy or something more I can easily understand. Like when I have an expression in terms of polynomials, because polynomials are, I find more friendly. Let's say I have 4x squared plus 5x on one side. On the other side, I have some unknown constant a times x squared plus some unknown constant b times x. And I think in order for this to be true, this equation, I have to have a to be the same coefficient as x squared, as 4, because they're both on x squared, and b equal to 5. Now that's because, x and x squared here are forming like independent basis for this polynomial space. Like, because x and x squared are of like different orders, they're like different types that we kind of talked about before. There's no way I can create something with a different combination of these that would work for any x other than having them match. So if I talk too much into this, I'm definitely going to screw up and say more wrong things than I have already. But for me, this is kind of something to think about, and just keep a tab on and see that it's correct, rather than going into it and saying every time that if you have coefficients on two sides of the equation, you can always equate them. I think in this case, because sine and cosine are orthogonal, that's fine. In the case of polynomials like x and x squared, x cubed, and stuff like that, each order of x is like forms the basis of the polynomial space. So it's the fact that they're like independent of each other that makes it okay just to equate the coefficients, is my thought process. So I think it's okay. I know it's okay. Well, I hear that it's okay. Like, you know, it is okay because somebody else told me it's okay. It doesn't really justify it. But as far as I think through, this makes sense to me. I'm not sure if it's correct. But it gives me some backing to what I'm doing. Right, I'm not just going to blindly go through this and equate coefficients without some kind of thought backing it up, some kind of rationale behind it. All right, another digression, but something that's important to me to think about. And if we get past this, when we equate the coefficients, we have two equations. We have the coefficients in front of the cosine being equal, setting up the first equation, and the coefficients in front of the sines being equal, setting up the second equation. So we just said this equals that, this equals that, and rewritten it down here. And from this, we can solve for the unknowns, which are A, the amplitude of this generic general sine and cosine that we plugged in as our guess, and the other unknown is the phi, which is the phase angle to our trial function that we plugged in. So when we divide the second equation by the first equation, we're going to get a tan of phi. And with a little bit of jumbling, we get L omega minus 1 over omega c over r is the tan of phi. And to get the A, the variable, the unknown A, we're going to do something that's a little less clever than we did earlier, but we're going to use this sine squared cosine squared sum equals 1 trig identity. And so to use that, we're going to square both equations and add them together. So omega squared v naught squared cosine squared plus omega squared v naught squared sine squared just gives us omega squared v naught squared, using that sine squared plus cosine squared equals 1 for the same angle on sine and cosine. On the right hand side, we square everything and add it together, so we're going to get all these squared terms coming out. And we can group the A term on the right hand side. We can divide out all the other stuff that used to go with A, put it on the bottom here, and we can take a square root of the whole thing. So doing that, we get to this point with all these variables, and doing one more simplification, we're going to divide omega from top and bottom, and when we put it on the bottom, when we divide it from the bottom rather, moving it through the square root sign is gonna make it divide by omega squared instead of just omega. And here it doesn't cancel out the omega squared directly because this whole parentheses is squared, so it's just gonna cancel one of the omegas. And this whole jumble of numbers gets us to the solution of the particular part. So this is rewriting what we started out as our guess, but the only difference now is we have an expression for the unknowns a and phi in terms of all the other variables that we've already defined as known. So even though there's a lot of letters here, all these are quantities or values that we already have. Now we can put the two pieces together and get our final solution. Final solution I of t is going to be the homogeneous part plus the particular part. So looking back at our homogeneous solution, we have a linear combination of e to the k1t and e to the k2t. Added to our particular solution, which is a sine omega t minus phi, combines to our final solution here, homogeneous part and particular part. And rewriting all the information that we've gathered below it, we have C1 and C2 are constants that are determined by initial conditions, which I don't really talk about. K1, K2 are the solution of the quadratic equation that we got from setting up the zero product property from e to the kt being always a positive value, and solving for k when we plug in e to the kt to the homogeneous equation. A is going to be the amplitude of this general form for sines and cosines that we use in the particular solution. Its value here we got from manipulating the equation with coefficients on cosines and sines. And the phase angle phi here is the tan inverse of this expression here that we also got from manipulating the coefficients on the cosines and sines. Omega is the frequency of the driving voltage that we started out with, so this is something that we specify ahead of time, so it's not an unknown. It is whatever we said it was to begin with. And so here in the equation, all the colored variables are things that we got from our solution that popped out as we were deriving the solution. T is our independent variable, E is our function. Sine is our function, omega is our frequency, and so all these variables are accounted for below here. When I first encountered this, I couldn't find a explanation for it for a long time. It was presented in E&M textbooks with the solution without really the steps on how to solve the differential equation. So that's really the motivation for me revisiting this problem and going through the steps and talking about it.